Yeah, right. Yeah, so this will be based on a paper. So you can take a look at for more details. But yeah, so the point of this model is that we are looking at the simplest possible quantum field theory, and we're trying to figure out when we don't have any particle production, and this is related to integral systems. And I think it will be more clear if I write down a Legendre so you know what theory I'm talking about. So let me start with that, and then hopefully it becomes a little bit more clear. So we start with the Legendre, half du phi du phi minus a potential, I should say Legendre density, and then it's the potential density. And it's in 2 dimensions, or 1 plus 1. And so that means that we have a metric in 1 plus 1 dimension, which we usually write as ds squared is equal to g mu nu dx u. And so here it will be dx0 squared plus dx1 squared. And I hope I have not lost anybody by now. No. Philip? It's okay. Yeah. So that's in 2 dimensions, and it is a good idea to use light cone coordinates. So light cone coordinates is where we rewrite the time and the x coordinate, x1 coordinate into x pluses and x minus. Oh, I forgot the d's. Yeah. And so concretely, this means that x plus minus is equal to t plus minus x over square root of 2. And you can convince yourself that if you plug that in to here, then you get back the metric that we like, the Minkowski metric. And of course, I can draw, I guess I should draw at least one diagram. So here, if we have, so in high energy physics, we like to put the time upwards, and x over here. So here we have x plus, and here we have x minus. So this is the light cone coordinates. Make sense? And oh yeah, and then of course x0 is the same as c times time, and c will, for this talk, be equal to 1, speed of light. Is there anything else I want to say? Yeah, so it turns out that, for instance, this kinetic term can be written in light cone coordinate as e plus phi d minus phi minus the potential. You can ignore this out. I see Philip is nodding, so I hope it is clear. Sure. Yes. Good. So the next thing is, of course, what should be the potential or potential density. And for the potential, we will write a half n squared phi squared plus a sum of n bigger than 3. Lambda n is a coupling constant, n factorial, the symmetry factor, and then phi n. So this will be our theory. So this is pretty general. So we have anybody who are not familiar with quantum field theory wondering why the mass term sits here in front of the quadratic term. So this is maybe you're used to non-relativistic, then the mass would sit in a different place. But in relativistic, it sits here. It will be clear in a short while why the mass term sits here. But this is one, and these over here, this is coupling constants lambdas, and we have infinitely many coupling constants. So, and we are asking, so we have an infinite dimensional space of theories, and we would now try to determine the couple constants such that there will be no particle production. And I will already reveal that it will be extremely restrictive. We will find there's only 2 1-parameter solutions. 2-parameter if you think of Mars as a 3-parameter. So it's extremely restrictive. So we will determine that. Anyway, so here, yeah, maybe before I go on, maybe let's do a little bit of dimensional analysis of this situation. I should be honest and say that this, we call it Mars, but if we have to be very careful with the dimension, then let's calculate what I would call inverse length dimension. So I want to calculate inverse length dimension. So inverse length, that's the same as the derivative, right? So derivative would have inverse length 1 dimension here, and the Legendre density will actually have inverse length dimension 2, because if we integrate over space-time, then we should get the action, which is dimensionless. Is this clear? Patrick is nodding. Good. So this would be -2 here and 2, so we get 0. And here we also have 1. So can anyone tell me what I should assign the dimension to 5 for this to work out? 0. It's dimension. We simply have to have the field to be dimensionless. And now we can then go down to the potential, which for the same reason must we have dimension 2. Then we see that this has dimension 0. Then we see that this has dimension 2. So this has inverse length dimension 2. So if I have to be completely honest, then this is not a Mars. This is an inverse length. If I really have to be very careful, then I would say that this M is really, I guess it's, is it? Okay, to write it. I guess it's M0 C over H bar. So then I get inference length. But I should say that this parameter is the fundamental one. This M is not fundamental, because I would not like to introduce inverse powers of H bar in my action. I would like my action to be classical. Okay? So this parameter is fundamental. It is really an inverse length, but I will abuse language and call it a Mars, because that's what we do. Is this clear? Okay, and then we can also wonder about what is the dimension of lambdas. 2. Right, and for that reason, I will now introduce lambda n to be the mass of times Gn. So I will define some dimensionless coupling constants Gn here. So yeah, and it turns out, so all our coupling constants have positive dimension here, and that turns out that then the theory is actually normalizable. So it turns out that the theory makes sense. All the infinities can be dealt with in this theory. So it will make sense. Anyway, let's go on. The first thing I guess you would ask is what's the Lagrange equations for this theory, and this will be Klein-Gordon. Plus interactions. So it will be something like minus nabla, I shouldn't say nabla, box phi equal to minus like this. Does this make sense? Patrick is nodding. Everybody can see that this is really Klein-Gordon theory with an interaction and a mini interaction. So we can,
Sure. To the previous point, maybe you said it, I just missed this. Why do you start at square, pi square, if you don't have pi to the first one?
oh, yeah. Yeah, that's a good question.
If you want to one later.
Right. I guess we could redefine what we call phi by a constant. You could move it, then you could get a constant term.
No, you meant the power of phi, right? In the potential.
The first power and potential.
Oh.
Why you start at phi squared?
Yeah. Right. Yes, that's well. Well, you can argue that this is actually a potential term. This is a harmonic potential. So Mikael, he actually knows some quantum theory, and he knows that we actually hack this together with the free part, the quadratic part. Here I organize it here also because it turns out that the end result would be nicer if I pack it this way. But yeah, so the point is that this is traditionally called interactions, and this belongs to the quadratic, will be the free part. So if you look at the free part, then and I would like to Fourier transform, then the free part will be k squared plus m squared Fourier transformed k equal to 0. Does that make sense? So this will be so now I have taken the mass term and into account, but all the other I have skipped, and then I'm solving this. This is called the free part. So there's dead silence.
So there isn't some like physical symmetry reason that you cannot have a linear term in the potential?
Was that the question?
Yes. Yeah. I was asking about the first power in phi.
Oh,
so what?
Yeah.
Why you
yeah. So yeah, but that is shift. So I guess you could shift phi to phi minus phi 0 or something like that. And that would create a linear term, for instance. Okay. So we have made a reduction such that we got rid of the linear term. Right. So yeah. Okay. So yeah, that was also what I first thought that you were asking about. Then I thought it was because of this a little bit strange division of potential, where I put the mass term inside V. Okay, anyway, let's continue. So here I have Fourier transform, and then the box becomes minus k squared here. Everybody agrees on that? So this here, so especially if you take this away, so the k squared plus m squared, this is called the on-shell condition or a Marshall condition. And the k squared is of course the same as minus k0 squared plus k1 squared. And so then you see this is just Pythagoras. So we can do another diagram here. So we have here we have energy, which is k0, and then we have momentum, which is k1, and then we have Lycone coordinates k plus and k minus, and then this on-shell condition becomes hyperbola. Here where we have an m and a minus m, and it goes like this. Does it make sense? And of course this when we have the energy k0 is negative, then we will talk about anti-part. So we have that. So now another thing that would be useful. So another thing we can do with the k-squared, because of the metric, then for similar reasons as this, then you can convince yourself that this is the same as minus 2k plus k minus. So this is the light cone momentum where we change into this. I see people are nodding, so I hope that's okay. So the other thing we can see is that that to be on the Mars shell, then we can parameterize. So we apparently have two-dimensional momentum vector, and we can now parameterize this to be 1 over square root of 2 times some parameter a and a minus first, where a is a free parameter. So put it in a different way, the momentum is a two-dimensional vector. We have one Mars shell condition, so that means we have one free number, so we can vary. So we can parameterize the hyperbola with a free parameter a. Make sense? And now we are especially interested in the analytic structure. So therefore, we're gonna let A become complex. But obviously, I cannot let it become zero. So complex different from zero. And the physical section will be when it's real. When A is real, then it's physical. But we will be very interested in knowing what's gonna happen in the complex plane of this A. Okay. So another thing we can do is we can look at Lorentz transformations. So what's the Lorentz group in 1 + 1 dimension? How many rotations? How many boosts? 2. The one. What?
That should be.
Yes, there's one boost. There's no rotation because there's only, you cannot rotate in one-dimensional space. So there's only a boost. That's right. And the boost is of course along here. And I don't know if you're familiar with light cone coordinates, but it's very simple to boost. So remember that A is essentially the same as k plus, the plus component of momentum. So the boost is just that you take e to the eta a, where eta is the rapidity. So that means the tangent hyperbolic is the same as b over c, sometimes called beta. So it is, we see that Lorentz transformations, which is the same as boost transformation, that is the same as a scale transformation. In light cone coordinates. So it's that's quite simple. Okay, so this was more or less the classical aspects. So now let's go quantum. Okay, so now we will, since everybody have not looked at quantum field theory, I will only do aspects of quantum field theory. So there is an object which we call the amplitude. And I will try to describe it, of scattering amplitude. So we usually think of it as something, an object which have n legs. So we are assuming that we have n particles coming in and out with some momentum. So here we have k1 K2 and up to Kn. And I will assume that for simplicity that we will change. I mean, of course, there will be particles coming in and particles coming out, but we will assume that all particles go out, but then we will have to assign some of them to be antiparticles. So we will, all the K's will go out. So we just can say that K1 plus blah 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 Kn must be 0 because of total momentum conservation. Like that. Okay. So that's the first thing. The next thing is that an amplitude is really a sum of Feynman diagrams. So where I would just write some example. So there will be what we call lines of propagators. And there will be vertices, n vertices. And so for instance here there will be some external legs and internal legs, and there will be vertices, and there will be some final rules that tells us how to interpret, make or transcribe or translate these pictures or diagrams into mathematical formulas. So there will be some. So here let me draw like this. I don't know this, and maybe later here something like this. So here, then there will be some rules. So this will be, for instance, this will be a propagator here, and this will be a loop, and so on. And the rules will be quite simple. So the line of the propagator, and this I'm not gonna explain, but we will just take this as some Lego building blocks, how to build up the theory. So there will be a propagator, and it's given by this expression, k squared plus n squared minus some I epsilon here. There will be some rule here where this is a regularization, and I will not really talk about that for now on. It's for Feinschmecker. For now, let's just take this. So that it will be some rational function in momentum, and it's given by that. And in fact, it is somewhat related to the free part of the Legendre. It's sort of the inverse of that. So that's the propagator, and the vertex is given by the n vertex is given by the n interaction. So that's we will just have to multiply the lambda here. Okay. And yeah, and then of course we will also assume that in each vertex there is momentum conservation. Should we call it local momentum conservation in each vertex? These two, or maybe together with it, this is called Feynman rules. So these are the rules how to convert these diagrams. You have to transform all diagrams into so there's some rules. So these are the rules. Okay, so and once we have set up this, then the square of the amplitude is given by a probability. And so roughly speaking, so you can think of these amplitudes as the same from quantum mechanics, where you think of a wave function, and you square the wave function, then you get a probability. So in quantum field theory, you have some amplitudes, which there are some rules to calculate, and the square of this it gives, roughly speaking, a probability of something happens. And we will not be so concerned about exactly how to normalize this, because we are in the game of finding out when there's no probability, when there's no probability. Good. All right. So let's what is no particle production? And by no particle production, I mean that certain diagrams are, or amplitudes are allowed, and some are not allowed. So the allowed ones would be that we have two particles going through like this here. This would be allowed. And or they could scatter off each other elastically. So this is allowed processes. What is not allowed is that you take one particle that becomes two particles, or two particles that becomes one particle, or two particles that becomes three particles, and so on. Does that make sense? So that's what I mean by the theory should have no particle production. The only thing is that these types are allowed.
You mean the number of incomes and outcomes is preserved?
Yeah, yeah. And not only that, they actually will also insist that the momentum is changed.
So is that kind of a nudger current associated to that, so that the the number of particles is constant?
Yeah, I guess so. I guess this is closely related to what people take as the definition of integrability, and where there is infinitely many conserved currents. So yeah.
What you see about this weaker condition, no? That the number of particles stays the same. Because you could have like three particles changing into one, and then one into three, and then that number will be the same. But the vertices that are not allowed. You have to have like if you look at the Feynman diagrams, you just disallow some of these vertices, and it's stronger condition than saying no particles, saying the amount of particles stays the same, or the in and out stays the same. Because you could have like mixed terms like that, and it could even out in the end. But what you're saying is stronger than that, right?
Yeah. Good. So, and then the other thing we would be interested in is singularities, because we're especially interested in, so the only singularities. Okay. The only singularities that we can come, that can be, is from poles from propagators going on shell. Okay. Actually, I see that I actually skipped one thing. So the first thing I should say before here is that we will not consider loop diagrams because it turns because loop integrations are very difficult. Loop diagrams are very difficult to calculate. But we can actually argue why we don't have to do it. And the reason is that if you calculate every time you have a loop, then it turns out that there will be an h bar power. So if this diagram, the value, mathematical value, would be proportional to h bar to the number of loops. And we will be especially interested in the limit where h bar goes to 0. So the classical limit. So in classical limit, we can forget about loops. The diagrams which are not loops, they are called mathematical trees. So we are interested in trees. And we will also, for simplicity, just look at the connected trees. Because all diagrams can be decomposed into connected parts. So we will just look at connected trees. And then there is some technicality that we will actually amputate them. Trees. So what does amputate mean? It means that for all the external legs, so there's external legs here, there's internal here, we will not assign any mathematical value other than 1 to those. So it is as if we have amputated the diagram and only look at the internal parts. So that will be the object that we're looking at. Okay? So connected amputated trees and rules, and then just put it together. And the result will be a rational function in momentum. And especially we see that the only way that can be poles are for the propagators to go on shell. So the only thing that can happen is that this denominator becomes 0. And by the way, you recognize this denominator as the on-shell condition. So that it is as they like very much something that's on shell. So then because when this becomes 0, this becomes big. This means that the amplitude becomes big. The probability becomes big. It is something that will happen often. Okay. So we will be interested, especially in singularities and poles from propagators going on shell. That's the only way that these singularities can arise. The other thing we already know is that the Feynman rules they are Lorentz invariant, because if you look at the Feynman rules, then you see this is clearly Lorentz invariant, this is Lorentz invariant, everything is Lorentz invariant. And Lorentz invariance means boost invariance, and boost invariance means scale invariant. So that means that the Feynman rules, they are scale invariant or the boost invariant. So that means that this amplitude is scale invariant. So we see that so we get an extremely important conclusion that says that if the amplitude, if there's no poles, then it's a rational function with scale invariant function. What can it be? Constant. It can only be a constant. So that means that an must be constant. So we will use this all the time. This is the trick. So we will try to get rid of all poles, and then we know that the amplitude must be constant. Okay, so that's one more trick that we have to learn about, and then we can start cases. And this is yeah.
Maybe a simple question, but sure. If we have more dimension,
Yeah.
we are taking just now one spatial dimension.
Yeah. 1 plus 1.
Yeah. So it's just moving on a line.
Yeah.
So how can a particle interact itself in just one dimension?
I guess the beat. So they are. If you freeze time, you have to freeze time, and then you have a line here, and then you have particles on a one-dimensional line. And the only thing that can interact is if the meet.
Yeah, no. I mean, how can a particle interact with stuff? Because you say that you can have also loops, right?
Yeah.
You're not taking into account the loops, but theoretically there is also the self-interaction. How can a field the self-interact with itself in one dimension?
Yeah, that's a good question. I guess first of all we are doing in the momentum space.
Just physically speaking, how is it possible? Yeah.
Right. Mathematically, there's no problem. I guess maybe yeah. Oh, but of course, the diagrams we're doing in space-time. So we are not really confined to one dimension. We're doing it in 2 dimensions.
Yeah, but it's like you're saying basically a particle moving on a line,
Yeah.
and in different times, say it takes different values on this line.
Right.
Basically.
But yeah, so I guess you probably are in space-time, but the way we usually do the amplitudes, we're doing it in Fourier space. So we assign some momenta coming in and out. So we are in momentum space.
Yeah, I mean, mathematically speaking, it makes sense, of course.
Yeah.
I just wonder,
right,
what does physically mean?
Yeah, that's a good question. But again, we're not really into numbers. Yeah. So maybe I'll go on. Then, so the last ingredient of quantum field theory is factorization. And this is a quite interesting phenomenon, which might not be obvious when you first think about quantum field theory. So if you have some amplitude with n legs, so you have here maybe kr k1, kr plus 1, and kn, then it turns out that if you take your particles, oh, that's by the way another thing. So I call it k here. This is of course wave vectors. So that's another instance where I call it momentum, but it is really wave vectors. But it's too difficult to say wave vectors, but they say momentum. But people also say momentum conservation, but of course it's wave vector conservation. You have to be really strict. Anyway, so here we have these momentum coming in and out, and we could now tune the first R vectors such that k1 plus up to kr squared plus n squared goes to 0. So in essence, as we tune these incoming or outgoing k such that this precisely becomes like what happens in a propagator downstairs in propagator. A propagator will blow up if this happens. The funny thing, which is actually true for quantum field theory, is that there is a factorization going on. So in this limit, obviously diagrams which contain such a propagator. There's a 0, let me just call it 0, 1 up to r here. Yeah, so what I mean by this symbol, I mean, of course, 1 over k1 plus kr to square plus n square here. So that's the formula for that one. That will become very big. And it turns out that in this limit, we only, the dominant diagrams is only the diagrams which contain such a factor. We don't have to now calculate all diagrams. We only have to take the diagrams which actually contain this diagram, this propagator. And the rule is that you just have to now attach 2 sub-amplitudes to the 2 sides. So here you have to attach one which have kr up to k1, and so it has 1 r plus 1, so it's r1 plus 1 here. And over here we have kr plus 1 up to kn. So now we have to calculate how much should this be. I guess the point is there's n legs altogether, but there's 2 more here, so it's n plus 2. So these 2 guys should sum up to n plus 2. So I should take n minus r plus 1. Does that make sense? Yeah.
So isn't it possible for a diagram to contain 2 of these propagators or 3 of these, which will make it much bigger than a diagram that contains only 1?
No, because so first of all, this is tree. So we are only talking about trees. There's no loops inside. And the point is that if there's 2 of these guys, so imagine that we have 2 of these guys here, and then there will be another guy here. I guess I'm allowed to maybe. Then I guess there could be some diagram in between. So you wonder if there could be something like this.
Yeah, exactly.
So the point is that that this number here precisely corresponds to from momentum conservation. So it is as the momentum from these R guys is inside this here. But if so, it will be okay for this one. This will be 1 to R. But there will be additional lines here. I guess so we cannot allow these lines here because then it would change. There will be another over here.
Yeah.
So we will not allow this.
And then it's a loop.
And then it has to be a loop.
Yeah.
And then we don't allow that.
Yeah.
So that good question. Now that cannot happen.
Yeah, thanks.
So this is really powerful because in some sense this maybe can help us build up bigger amplitudes from smaller amplitudes. So we get some kind of recursive direct loop. Very annoyed.
No,
Yeah.
I just wanted to ask if you use that symbol delta with 1 up to R,
Yeah.
then do you just need some mess of those lines somehow crossing one another, like in that way? I don't know how to imagine what kind of diagram makes sense.
So you mean this notation?
Yeah, I mean that whole thing that you use to connect those 2 amplitudes.
Yeah, I mean, because this notation here, I would guess, if I had to connect with the notation upstairs, then I might be tempted to call this delta 0 of k. so the logic tilde means that it's Fourier transform 0 for the three parts. And so this notation here, I guess I should really expand as K1 plus KR. So this notation is just a substitute for this string. So that's there's nothing there.
So as a picture, it's just one line.
Yeah.
But
Yeah, it is just one line. It's just one line. Yeah.
And doesn't it contradict the rule that we don't want to allow the situations where we don't have equal amount of lines coming in and coming out?
No, because it's notation. I'm renaming it's just you can think of this as a line here, but the momentum which flows through the line is which we would call K, happens to be a sum of external particles momentum. So it's just a single K. Yeah.
Maybe the factorization is quite general property of arbitrary entities. It is not related to no particle production.
Yeah.
So the factorization is really general requirement actually of scattering entities.
Also
that.
Yeah, true. That's right. That was a good point. Yeah, it has nothing to do with no particle production. This is a general property of yes. And then, of course, we will now impose this condition. And what does that, for instance, mean for factorization and so on? So that, sure. Yeah?
You have those, there are two propagators. And I understand there cannot be like two propagators that are the same, that means roots. But we can also factorize, for example, R or amplitude R plus 1, right? We can split
this one,
and make it one more, but there will be two different propagators in down there. It would be like from if we do it to, for example, I to R, R to M, right?
Oh, you want to also factorize this? Yes.
Yeah. For example, so there will be two propagator lines and.
Right. So the point is that we are imposing this condition here. To begin with, but you are welcome to maybe impose more conditions.
Okay, I was just wondering.
And then have more cuts, so to speak.
Yeah, I understand.
We will only need one, but so that's true. Okay. So I hope it's clear that the point is that we engineer the external momenta such that this combination happens to be very small, so that this propagator becomes extremely big, and that means that we can forget all diagrams which doesn't have this propagator, and it happens to be such that we have to include all the diagrams that we have to include happens to just make up as an amplitude of smaller number of layers. That's not at all clear, but this is a property of quantum field. So that's quite nice. Okay, so let's now continue with. So I guess I got to this one. So now I will call something I call a true propagator. And later I will call something I call a free propagator. And that may look a little bit strange because I know a propagator has two ends, right? It starts and ends. So what do I mean by a true propagator and a free propagator? That doesn't make any sense. Well, what I'm trying to say is I'm thinking of a propagator, so I will call this an R propagator because I have the momentum coming from three external legs flowing through. So the point is, I will think that there's momentum from two external legs, Ki and Kj. And then I'm looking at delta 0 tilde ki plus kj. Yeah. And then I, for some reason, want to normalize this with a factor minus m squared multiplied with that. So this is just a normalization factor, and then I will call it for delta ij. And this becomes according to the rules m squared over ki plus kj squared plus m squared. And so this is the same as minus m squared over minus 2. So I guess I already deleted my metric, but it will be k plus I plus ki plus kj, or it would be j ki minus plus k minus j plus m squared. So this is the metric, this minus 2. And you can convince yourself that this is the same as 1 over ai plus aj, ai minus first plus aj minus first plus minus 1. Yeah. So this was how we translated from the plus momentum into the a's with some factors of the m's. So we get this, and then you can simplify this, and it becomes ai aj over ai squared plus ai aj plus aj squared, like this. And what we're interested in is poles. So now we want to know what are the poles of a propagator a true propagator that has momentum of two guys. And so therefore we want to factorize this. And after a bit of thinking, then you realize that this I can factorize as ai minus e to the 2 pi I over 3 aj times ai minus e to the minus 2 pi I over 3 aj. Okay, so we learn that the poles in the complex plane of a true propagator is given by ai is equal to e to the plus minus 2 pi I over 3 aj. So this is where we can have a singularity in this, and we see, by the way, it's unphysical. We can never have a, so this is one of the reasons why we go to the complex plane to pick up these poles. So this is an unphysical pole. Make sense? So now I'm getting tired of these factors of m. So for now on, we will simply say, okay, let's do dimensionless units. So that means that C is 1, H bar is 1, M is 1. So especially we will only be interested in the massive theory. So we will not talk about what happens when mass goes to 0. So we're talking about a massive Klein-Gordon theory with interactions. Okay, so the tree propagator goes very similar. So now I have 3 ki, kj, k here, and so now it will have delta ijk equal to minus m squared, but so it becomes minus delta 0 of ki plus kj plus kk tilde. And maybe I will just give you the result. The result is beautiful. It turns out to just be ai, aj, ak divided by ai plus aj, aj plus ak AK plus AI. Very beautiful formula. So what's the singularities? It's already in. Yeah. So the singularities opposed are just that AI plus AJ is equal to 0. So they are opposite. So it's like an incoming, outgoing kind of thing. So that's why we have the poles. And just for fun, let's also calculate the recipe of this guy. So the recipe will be AI plus AJ for lim AI plus AJ going to 0 of AI plus AJ times delta ijk. So I'm just multiplying by that. And then you can convince yourself that that's going to be AI squared AK, AI squared minus AK squared, I think. Sorry, I'll leave you to ponder that. So that's propagators, two propagators. And now we can start, yeah?
I'm probably stupid, but where did the a to the power of 2 pi I divided by 3 came from? I don't see.
Just multiply it because that cosine of 2 pi over 3 is minus 1/2.
Yeah.
It's just a solution of the quadratic equation.
Yeah. Yeah. It's difficult to see directly, it's easier to see backwards, as Derek points out. Just multiply it out and see that we get back what we want. Okay. Okay, so the plan was then to just go through, starting with 3-point function, and write down the number of amputated connected tree diagrams of the 3-point function. So there's 3 external momenta. What diagram can you think of which connected 3? There's only one, right? There's the only thing we can think of is this here, K1, K2, K3, like this, and lambda 3. So that's the only tree diagram we can think of. And so the rule is now to there's some convention factor I over h bar A3 is given by, and there's a rule minus I times lambda 3, and you get rid of this, then it turns out that A3 is just minus lambda 3. So that is the first here. Okay, and then you can wonder, we're not allowed to have A3 because this would be like 2 to 1 or 1 to 2. So what then? Well, then, but we should also check the momentum conservation. So the momentum conservation say that A plus and K plus and K minus should be 0. The sum. So we get that A1 plus A2 plus A3 should be 0. And A1 minus first plus A2 minus first plus A3 minus first should be 0. Do we agree about this? This is momentum conservation in line coordinates. And we have to make sure that this is satisfied. So this, we have 3 complex variables and 2 conditions. So this is a 1-parameter solution, right? And I will just give you a solution. It's straightforward, nothing. So the solution is that A1, A2, A3 should be what I like to call a Mercedes-Benz diagram. So you have here 1, here you have e to the 2 pi I over 3, and here you have e to the 2 pi I 3 minus, like this. So Mercedes-Benz, and the solution is going to be proportional to 1 e to the 2 pi I over 3 plus minus, or minus plus e to the 2 pi I over 3 times a arbitrary coefficient in front. You can check that this obviously satisfies this condition, and you can also check this the whole solution. Okay? Philip?
Yes. First or second?
Both. That was easy. So 3 unknowns, 2 equations that give us 1 degree of freedom. That's the proportionality factor. And the point is now that the A's are never going to be all physical. So this is unphysical. So we see that the amplitude is unphysical. So even though it's non-zero, we don't have a physical center. So we can forget about it. Yeah?
Can I ask a question?
Sure.
What's exactly the position of plus minus is in the vector?
Opposite. Yeah, it should. That should be. Oh, it's too fast. It should be minus plus. And it should be e to the plus minus. Yeah. Yeah. The point is that I don't know which one's first and second. So I have to do like this. Yeah. Good question. Not just good. Good. So that was easy. So let's. I hope you're still. Think let's go with four points now. So which diagrams can we draw with 4 points? So I can guess lambda 4 now, and then I can draw this one, lambda 3, lambda 3. Right? There are 2 diagrams. So now we have to write down the solution. So I'm just going to write down A4 is given by. So don't worry so much about the sign convention of these sign conventions. But there is a sign. There's some kind of alternating sign going on. So it's minus lambda 4 plus. So that's for that diagram, and then there will be for the other diagram. It's a little bit more complicated because we don't know which legs. Belongs to which legs, so we actually get 3 contributions. ST and U channel will expert call it. So, so it's something like delta 0, 1, 2 plus delta 0, 2, 3 plus delta 0, 3, 1. Like this. So, and this has to do with that you can have 1, 2, 3, 4, but you can also have 1, 2, 1, 2, 3, 4, or you can have the last one. I guess it's something like this: 1, 3, 2, 4. Does that make sense? So you have to take into account all ways. You don't know, don't know if the internal propagator. You don't know which 2 it's between. So you have to take all of them into account. And there's 3 possibilities. So you get 4 diagrams altogether. Yeah.
Another stupid question: why don't we get anything with the 4 in there? What's so special about the number 4 that it doesn't appear?
Yeah. It's related. It's a good question. Is not all stupid. Yeah, in fact, I think maybe it would answer your question when we talk about the momentum conservation. So let's check the momentum conservation for four. Yeah. So now we have A1 plus A2 plus A3 plus A4 equal to 0, and A1 minus first plus A2 minus first plus A3 minus first plus A4 minus first equal to 0. Like this, right? So now we have four variables, two conditions. So now we get a two-parameter solution, right? And again, this is elementary, so that's homework or whatever. I mean, that's an exercise that everybody that has 15 minutes to spare can work out, or 5 minutes. But I will just give you the answer. A1, A2, A3, A4 are two pairs of opposite values, AI plus AJ. So it turns out that momentum-wise, you have something like 1, 2, 4, 3, or 1, 2, 4, 3, or 1, 4, 2, 3. Make sense? I mean, by this, I don't mean Feynman diagrams. Here it just means that the particle 1 and 2 have opposite momentum and so on. So it basically means that momentum-wise, we can transfer momentum from one particle to another. And that is exactly the condition for interoperability or for low particle production. So even though this is a complicated amplitude, if you work out that it has complicated poles and stuff, it turns out that the momentum again savors, the momentum conservation again savors. That's only allowed the thing that where the momentum is conserved. And so to go back to Derek's question, the point is that when we're talking about an endpoint amplitude, then there's two conditions. So instead of depending on n momentum, first of all, there's on-shell conditions. So we start with 2n momenta that become n momenta because we take away, we have the on-shell condition, n on-shell conditions, right? So we have, it depends on A1 up to AN. But then there is momentum conservation, which takes away two ANs, AIs. So it depends on n minus 2. And the point is that I, behind the scene, choose this because I thought it was a nice pattern. But I would choose, I know I can switch because of momentum.
Essentially, the fourth momentum is minus some other momentum.
Absolutely right. Absolutely right. So you can get it in any completely symmetric form. Very right. Good. Okay. Are you still? I see Philip 2 is. Okay, so are you ready to go to 5? So let's move on.
Yeah.
Okay, so now let's do 5 point. Okay, so what diagrams can we have for 5 points? So I guess there will be there will be lambda 5. And what else? So I guess there will be one something like this. And then I guess there will be something like this. Oh, I guess that's too much. Is this better?
Yeah.
I think this is it, right? And let me also put some. So let me call this I, J, K. So there's a lambda 4 here. There's a lambda 3 here. There's a lambda 3 here. Lambda 3. Lambda 3. J, K, I, L, M. Like that. Okay, so I claim that if you write down A5, at least in principle, it will be. So now it becomes a little bit more annoying. So we will see, even though I only have 3 different topologies here. Same way we only have 2 different topologies up here, but we got 4 guys different here. Then of course we will also get more here. So the point is that here we will actually, there will be these two are special. So there will be 2 over 5, 10 diagrams of this type. Okay? This guy is special. There will be 5 ways to choose that. And then we have to choose 2 out of 4. So then 2 out of 4. But because of symmetry, we have to divide by 2. So this is 15 diagrams. So that's 26 diagrams. So it's a little bit too much to do now. So I'm just laughing. Okay, anyway, so the point is we have lambda 5 here. That's the first diagram. And then this one is lambda 3, lambda 4. And then a sum of I, J, K belonging to 1 up to 5 of where I, J, and K are ordered. And then we have delta 0, I, J, K here. So here, this is this diagram. So here we see we have 3 propagators. So by the way, all of these can be viewed either as a 3 propagator or as a 2 propagator, depending on which order. This can be used as a 2 propagator or a 3 propagator from the other side. Does that make sense? So this is a 3 propagator if we think from that side, and it's a 2 propagator from that side. And of course, that's the same because of total momentum conservation. And the same here, this can be thought of as a 2 propagator from that side, but if there are 3 from the other side, and vice versa.
Wouldn't it be like propagator times propagator?
Yes, there's 2 propagators. There's 2 propagators here. But each propagator can either be thought of as a 2 propagator or a 3 propagator.
I think like because it's symmetric, so
yes.
you could write it even from there as a 3 propagator. No?
Yeah, if I take from that side, then this would be a 2 propagator and this would be a 3 propagator.
Or you could write it in the middle vertex, and it would be 3 propagator or 2 propagator, right?
No, I cannot do that because I have to divide into what's on one side of the propagator and what's on the other side of the propagator. So, because I'm talking about what flows through the propagator. So I know that whatever flows in must flow out. There's total momentum.
Yeah, sorry. Yes.
Okay, so this is this diagram, and then the last diagram. I think I have no space here. Would be lambda 3 to the cubed because there's now 3 vertices. And then divided by a symmetry factor. This is the first time we see the symmetry factor because this diagram actually has symmetry. So we need to divide by 2 here, and then we get I equal 1 to 5. Sum over J and K should be different from I, and J should be less than K, and then we have to sum over all L and M, which are different from I, J, and K, and L should be less than M. And then we have two propagators, I, J, K, and delta I, L, M. So this is the formula, and of course it will be quite messy to write out all 26 terms, but we have actually, this is the formula, right? So now we would like, first of all, it's a 5-point function. So if we have no parsing production, we cannot allow this at all. Now we actually have 5 variables and we cannot rely on momentum conservation anymore. This is not going to save us anymore. We really need this to range. So this, so now what the tactic now is, okay, let's do it in 2 steps. Let's first get rid of all poles, because if there's no poles, then it's a constant. And so that will be the first step. Let's do that first. So the strategy is to say, okay, idea, analyze possible poles. And we know already where the possible poles can come from. They can only come from the internal propagators. And this is why we notice that all the internal propagators can be viewed as free propagators. That's nice, because then we don't have to do this on physical stuff with the 2 propagator when we have this e to the 2 pi. Now for the free propagators, it's just opposite. So we just have to look at AI plus AJ equal to 0. This would be enough. And then because of symmetry, we just have to take A1 plus A2 equal to 0. We only have to look at that pole because of mod S5 symmetry. Because the whole amplitude is symmetry on this permutation. Okay? So we just have to check this. And so the point is now that we should calculate the residue, which is lim of A1 plus A2 going to 0 of A1 plus A2 of this amplitude A5. Yeah. And this I could do, but this would take me at least 1 hour. So I think you get the idea, and I will just give you the main point, okay? You can read it in the paper. There's several sections to do that. It turns out that the result of all the 26 diagrams, the residue of that, becomes something proportional to G3, G4 minus 3G3 cubed. Here. G square. Yeah, the cube is 1.
Is lambda over M squared.
And yeah, T was where we have subtract is lambda divided by M squared. Yeah, exactly. Yeah. So that's and of course you can check this. This of course comes from this guy, and this comes from this guy, and this has no poles, so sort of makes sense at least. So, but this is that's a very interesting result, because we need so the logic is now the following: no particle production, means that A5 should be 0, and if A5 should be 0, then we see that there should be no poles, and then this have to be that either it's because G3 is 0, or it's because G4 is equal to 3G3 squared. So now we get strong conditions on the quartic and cubic interactions. Either there's no cubic interactions or they're related in this way. So that's very interesting. But this only gives us that A5 has no poles. It's a constant. And then the trick is now that we can now adjust lambda 5 such that A5 is 0.
Yeah, I agree.
Because it's just here.
Yeah.
So whatever constant this is, we're just going to change A5 to get rid of that. So we fix A5, so that A5 will be a function of or lambda 5 will be a function of G3 and G4. Okay? So now that is A5 is 0. Make sense? Okay. So then we go on. 6 point. And okay, I promise you. Actually, what is quite interesting is that this proof is it always requires a new idea. It's never boring. If you notice that every step is a new thing. And you will see now that I will not go to A37 today, right? I mean, there will be a trick, so we get there faster. But anyway, A6 is still very interesting, but there will be new complications there. So I don't know how much time we have. Maybe we'll say A6 today and then maybe stop or something like that, and then continue another day, depending on what people think. Or maybe the suspense is too much, they want to know A7.
I just don't turn it to the advanced quantum field theory like 1 year ago.
Yeah.
With no 3 hours to go break.
Yeah. Right. So okay. So 6 points. So what diagrams can we have? I guess this one. Yeah.
So this we are saying that there is no algorithm for endpoint particle.
There will be from this point, but it turned out that the 5 point was very non-trivial, and the 6 point is also going to be non-trivial. And then afterwards, we will find induction. But we have to go to 6 point is still non-trivial. So we have to look at all the diagrams. So let me first write the one. So let me just write down. We have one here, which is like this, and then we will have something like this. And then we will have some Mercedes-Benz like stuff like this here, and then we will have this. And then we'll have this, something like this. And what else? Then there will be this. Like this. Right?
If you have like 3 line and 3.
3 line and 3.
This is the one in the
That's the left bottom.
Yeah.
Yes, I see.
Yeah.
Yes.
I think this is everything. Anybody objects? Now is the time. Actually, with 2 months before when I'm submitting. Okay. So the funny thing now is that you can think of this as a two propagator. This is a 2 propagator. This is 2 propagator. This is 2 propagator. 2 propagator. 2 propagator. This is a 3 propagator. This is a 2 propagator. This is 3. This is a 3. This is a 2. This is a 2. So we are still in. We have analyzed 2 and 3 propagators, not 4. so we can still do our analysis with respect to pole structures. So this is nice. Okay, we still so we have this, and the first thing we're gonna ask: are there any poles associated with two propagators? Let's take that first. And here we can do a new trick. So the point is that we can look at A6, and then we can try to if we have a true propagator. So if a true propagator is a pole, then it blows up. So we have a true propagator here, and then so that means that we need an A3, and we need an A5. Like this. Does that make sense? So we are, so the point is we are analyzing when something becomes dominant, the true propagator, we have a pole. This is exactly factorization. So we're looking at this blowing up, this true propagator. And then we look at this guy. We know what that guy is. It's 0. So therefore, this is 0. So we see there cannot be any poles associated with true propagators. So we have done the work already for true propagators. Nice. So that brings us to the next question. Are there any poles associated with propagators? And it turns out, yeah, so the trick would then say, okay, why don't we, this was so nice, maybe let's do factorization one more time. So, so the idea is, let's take factorization. Does factorization work? The 3 propagator, A4, A4, and that. And the problem is that
Why are we starting with A5 on the last one? Okay.
It's just because I was the other way, but you are, so that's good. Good, A6 here, and then so we have that. Now, so now we could think of, we can think of a single, what should we call it, single AI plus AJ. So we know first of all that the 3 propagators, we know that the singularities of poles are associated with this factor here, but this flows through here. Then the point is now that I guess I could be more specific. I could say A1 and A2. But then there will be a third guy, and the third guy can be any one from 3, 4, 5, and 6. So it turns out that the problem with factorization is there's not a single factorization channel. that if I take this, if this blows up, then there will be other propagators. I mean, it's this, for instance, if this is 1, 2, 3, this will blow up. But I can instead of 3 put 4 here, and that would also blow up because and so on. I don't have a single propagator. So the point was for factorization to work. Then I have to make a combination of external momenta such that I uniquely specify an internal propagator that blows up. But here we have competing propagators blowing up, so we don't have factorization. So that doesn't work. And then you can think, then you can start to become be smart and say, aha, okay, I know that actually the tree propagator it has 3 factors on that. Why don't I make as maybe the two things go on maybe a double pole, and then you can realize that you still have too few momenta that will be other, so you don't get a unique channel. It doesn't work. So you have to bite the apple. We say in Danish. You have to do the work. There's no we cannot just do a simple factorization argument. We really have to calculate. Okay. There's one thing. So this does not work. No unique factorization general. What we can do is we have to look at diagrams, but we can at least take away the diagrams which doesn't have a tree propagator. So we don't have to do all 7 diagrams. We only have to do the one with the 3 propagators. Right? So that's nice. So let's just calculate the ones which contain the 3 propagator. Because that's the only ones which we want to take the residue. We want to find out the residue of A6 that can only come from these diagrams. And it turns out that these diagrams here, when you put in the symmetry factors and so on, they organize themselves in an extremely nice pattern. It turns out that it's going to be, this is going to be a half sum over ijk from 1 to 6, I less than j less than k. And then it's equal to A4 ijk, delta 0 ijk, A4. Sum of LMN different from IJK, L less than M less than N, A4 LMN. So it turns out that these, when you break down this, then this guy becomes part of a 4 diagram. And this too, this is also part of the 4, and it organizes itself just to be on this form. So this is quite nice. And so once we have that, then the next thing is we're gonna consider a pole, possible pole, and we can just look at A1 plus A2 because of S6 symmetry. So we just have to look at this pole equal to 0 and check what that is. And when we do that, then because A1 plus A2 have to be 0, then you can, and we have these 6 momenta, then you can convince yourself that the other 4 momenta in itself have to satisfy momentum conservation. Because if A1 and A2 are opposite, then A1 minus first and A2 minus first is also opposite. And therefore, actually, it turns out that the momentum conservation splits into two momentum conservations. So we get actually, for the other four particles, we also get momentum conservation. But we already know what momentum conservation for four particles means. It means that A3, A4, A5, and A6 must be two pairs of opposite of AP plus AQ equal to 0. Does that make sense?
Yes. Yeah.
That must be the case, and therefore we can now simplify this into we get that this is equal to sum of k equal. So this is equal to sum of k equal 3 to 6 of A 1 2 k delta 0 1 2 k tilde A4 A, and then here we have LMN different from 1 2 k A4 LMN. Like that, yeah?
The way that sum has only one member in it, right? So, or does it have more? Because I'm a bit confused why you use the summation sign at all. Because it looks like L and N are the other three numbers. That
yeah, you're right. Yeah, as only. Yeah, here, that's right. There's the sum is extremely simple. There's only one term. Yeah, you're right. Yes. Good. So now we calculate the residue, and the residue becomes equal to. By the way, so the point is that 1 2 could sit over here, or it could sit here. And that's the factor half here. So I put it here, so it's always this side. So the residue now becomes A4 1 2. So now again we're using direct comment here that A4 only depends on two momenta. So it doesn't really depend on K here because it depends on A1 and A2. So we have A1 2. Sum of k equal to 3 to 6, residue of delta 0, 1 2 k tilde A4, and here we can put all of the other one, 3, 4, 5, 6. That doesn't sound right.
You didn't show yet what k is, so it's.
K is from 3 to 6.
Yeah, I know, but you can write 3, 4, 5, 6, 6.
Yes, because it doesn't.
It depends on
it doesn't
K.
depend
on k.
on K.
Yeah.
So the point is basically that this here we calculated before. It's A1 2 AK over A1 squared minus AK squared. Sum over K equal 3 to 6.
Yes.
So the idea is that we get 4 terms with 2 opposite pairs. So k can be from 3 to 6, but we know that ak are two pairs of opposite variables. So therefore, we would get two terms which are opposite, because this is the first power, this is the second power. And therefore, they will cancel 2 and 2. So therefore, we get that this is 0.
I would just say you are probably like A4, 1, 2.
Yeah.
So A1 squared would probably be in that amplitude of 4, depending on momentum 1 and 2. No?
Yeah.
It's
Yeah.
just.
Yeah. Yeah. Yeah, I think. Yeah, I think
Like it can be there. It's just.
Yes, but I don't know which of the 6. The point is I don't know which of the 6 it is.
Yeah, I understand. Yeah. Yeah, this is not just for A1, A2. I understand the residuum is more general.
Right.
I understand. Sorry.
So the point is that that for the 6th point, when we have the tree propagator, the tree propagators, they organize like this, and we get a tree propagator in the middle, and we have to sum over effectively 4 different cases, and they cancel 2 and 2. So there is no poles. And then we use the same argument as before. We say no poles. It means that A6 is constant, and then adjust A6 and lambda 6 so that A6 is 0 by the same argument. Okay, so how is it going with time?
Almost 4.
Almost.
It's almost 4.
15:25.
So what should we take 5 minutes more and then call it a day?
Sounds okay.
Yeah. So then if we allow 5 minutes more, then we can actually finish the induction, because then it turns out that the last one n bigger than 7 it's equal to 0. Now we can actually use induction. So we will use induction and say, okay, let's assume that a less than n is 0. And then we are going to look at a n plus 1. And then we're using factorization, so we know that that's AR, delta, maybe delta, and then a n minus or plus 3 minus r, I guess something like that. So we're using factorization. And then the point is that if this is bigger than 7, then the sum here must be of these two numbers must be bigger than 9. And that means that one of them is bigger than 5. And one of them is also smaller, both of them actually is smaller than n here. So we know by that this is already 0. So we know that at least one of these two guys are 0, and therefore we can get this. Yeah.
How are you justify that this factorization exists? Because here you have the problem that
Right.
it was not
Yeah.
unique.
Yeah. Yes. So yeah, I don't have a good argument. So the point is that when you get up higher, then there's not the issue with kinematics that you get. It becomes the higher up the number of legs, it becomes more unique DNA wise, right? I mean, it's the coincidence are in low number of legs.
Yes.
So that's.
I see.
Yeah.
Okay.
So that's the point. So therefore we know that a n plus 1 cannot have poles, and then we can adjust lambda n plus 1, and then get this. So at the end, we see, to end today, and maybe tell what we'll do next time, is that today we noted that there is, of all the infinite coupling constants, there's only there's only two one-parameter solutions. We haven't figured out what it is, but this we'll do next time. I can already maybe take away some of the suspense and say that one of them will be this time since Gordon one. But there will be one more.
Yeah, so I don't understand this argument, because every time you go to some an, you just adjust the lambda to be equal to whatever this amplitude is equal to, so it cancels.
Yeah.
But you don't know what it's equal to, so.
Yeah. So
how is that like a one-parameter family?
Yes. Well, it is a one-parameter family. It is adjustment. It's just that we didn't explain how to do it.
Well, it looks like.
Yeah. So next time we will do the calculation. Next time we will actually show what this what the adjustment is. Now today we have just shown that it exists.
Well, okay, yeah, but you didn't show that it will depend on some parameter.
Well, yeah. I mean, it could be that it doesn't depend on.
Yeah, it could be just
yeah,
some random
but in worst case, it will depend on lambda 4 and lambda 3.
Oh, I see. Okay, yeah, that's true.
Does that make sense?
Yeah. I see.
Okay, so I guess we'll stop here and then continue next time with actually determining the higher lambdas from the lower ones. Yeah, if that's not enough, I can put it forward.
Yeah, sorry for the trouble. It seems like I don't know if they changed it or something, but we couldn't have the Zoom meeting for more than 40 minutes. So we had
I
to.
guess the pandemic is over,
Yeah.
so
Okay. The Zoom, well, I fear that the audience will be my worst enemy, but the Zoom was.
Thank you.
Yeah, thank you.
I'll let you know about next week another time. So, do you have any time restrictions for next week? So we will do it next week.
Sure. Yeah.
And then I'll send the rule.
Yeah. Let's do it as quick as possible so people don't forget.
Yes.
Sure. Okay. Yeah.